So hi, my name is Ram. I will be talking about making loop access analysis more precise. I work at CoderSip, and first we'll begin the presentation with what loop access analysis is, because many of you probably aren't familiar with what it is exactly. So loop access analysis was actually built for loop vectorize. That is the primary reason why loop access analysis was built. And among the other users, there are some other users, SLP vectorize for instance, but it doesn't use that many features of loop access analysis. It's not a very heavy user of loop access analysis. So it's a dependency analysis essentially, which is built on scalar evolution that tries to prove that something is legal to vectorize, or is legal to vectorize with runtime checks, or I just don't know the dependency, and the dependencies are unsafe, and therefore don't vectorize it. Among the other users, there's also loop versioning, which I will talk about briefly. It versions the loop, so I will talk about what this versioning is. And there's loop load elimination, which uses the versioned loop per se. So these are the users, and of course there's loop distribute. Loop distribute is not turned on by default, although there is the equivalent in GCC, which is ldist, which is actually quite powerful. So we should wonder why our loop distribute is not as good as GCC's, and whether it can be useful for vectorizing some additional cases. So the reason, I would say that loop access analysis was primarily built so that it can emit runtime checks. And here you see that you have a const float star x, const float star y, which means that you don't know if they alias. So if it does alias, there is a problem with vectorizing this. And the reason loop access analysis was built, and the primary thing that it does, is it communicates what runtime checks are needed. And loop vectorize synthesizes these constraints. It's basically a scalar evolution expression that it uses scalar evolution expander, and it synthesizes these constraints, and it says that, these are runtime checks. If it's not satisfied, then don't vectorize it. If it is satisfied, then vectorize it. So of course, if you make the float star a float star restrict, it means that it doesn't alias, then it's just trivially safe. That's fine. Loop access analysis will say it's just trivially safe, and that's totally fine. But it can also perform like non-trivial analysis. Here's an example of a non-trivial analysis. This is like, it determines that this is safe, because I've actually taken 2 times IV, because if you take IV is equal to IV minus 1, what happens is that it does mem copy. It synthesizes it into a mem copy. So I just made it 2 times, so that for the purposes of you being able to check out the example. So what is a dependence? A dependence is there between a load and a store, or a store and a store. It's never like you're just reading from some memory and there's a dependence. No, that's not a dependence. If you're reading from memory, if you're only reading from memory, if it's a read-only loop, what is the dependence? There's no dependence. But if you're storing 2 conflicting parts of memory, then that's a dependence. Or if you're loading something and you're storing something, in a manner that either has some kind of loop carry dependency or some kind of indirect unsafe dependency in loop access analysis terminology, then that's a problem. So let's look at what a forward dependence is. So this is a forward dependence. I've written a plus equals over here so that it emits the forward dependence. Here, what does it mean? It means that this IV, this induction bar, is like given to the previous value is now given to the next value, which means it should be vectorizable. This should be vectorizable. But let's look at a backward loop carry dependency. And here I've used something called a stride. So stride is basically some kind of constant or some kind of symbol that is multiplied with the induction var. So you often see strides in real-world programs. Like the induction var is multiplied by. So for instance, in the previous example, in this one, the 2 times was a stride. So that's a constant stride. In this case, it's a symbolic stride, which means that it's some variable that it knows it's a symbol, but it doesn't know what it is. It's like you have to. It's like an argument to the function or something like that. So in this case, what it does is LoopAccessAnalysis also performs the other function, which is to version the stride. So it generates a version of the loop with stride equal to 1, and a version of the loop with stride is just symbolic. So this is what loop versioning uses, and this is useful in certain cases. For instance, loop load elimination. So let's look at these variations, okay? These are interesting variations because these are actually not vectorizable. But LoopAccessAnalysis is not, this is an example to illustrate that LoopAccessAnalysis is not really a full dependence analysis. It's not like, it's a freestanding dependence analysis that will tell you the dependencies of all the dependencies in the loop. So it's only going to tell you, like, I mean, in these cases, okay, I mean, you can ask what is the utility of telling me the dependence if it's not vectorizable anyway? But I mean, if it's not vectorizable, I mean, the LoopAccessAnalysis is a freestanding analysis, right? So it should give you a dependence analysis. But I mean, I don't know how we want to approach this. We can say that maybe it's good enough in practice, and it just reasons based on simple Skev expressions. It works in practice, and it is like good for vectorization. That is, it's like, okay, it works in practice. It's not good in an absolute sense, but it works for most cases. So this is the very illustrative structure. Actually, this is what it internally uses to communicate what information it has dug out in terms of its analysis. There is a dependence distance, which is basically, if it's IV minus 1 and IV, it's 1, or something multiplied by the type byte size, which is basically, if it's an int star, then the int star size times 1. But I'm not going to get into the details of that. So the type byte size is essentially the like I said, the size of the pointer, the underlying variable. That is, if it's an int star, then it's the size of how much that int star will increment with every +1. So that's what the type byte size is. Then there is a max stride, a common stride, a should retry with runtime check. So what is all this? I mean, like, so if you look at it over here, there is only one stride. And what does this mean? I mean, like, why is there only one stride? I mean, is everything like, if I write multi-indexing, is there just one stride? I mean, is there only one constant or one symbol that is multiplied by an induction var? Are there no other induction vars? But there is only one stride for LoopAccessAnalysis, and this is very illustrative. So I mean, you would say, okay, what is this? I mean, like, is this some theory or something like that? No, it's not. It's just, we found that, yeah, I mean, this is the most obvious way to like subtract Skev expressions and say that we want to communicate whether we should retry with runtime checks, what is the max stride, what is the distance, and we can tell what is the dependence, therefore. So like I said, the dependence distance is just a Skev minus. But again, you have to ask yourself, if you do the Skev minus, so that Skev is something that does not use arbitrary precision integers. So this means that there is a certain bit width associated with it. which means that, if you have ever experimented with it, it's like skev, you usually ask for the trip count. It says, yeah, it's some sign extent expression or some zero extent expression. There'll be some cost, there's going to be some cost, and then plus 1 of the max backage taken count. So there are costs. There are costs in skev expressions. So and so if you do minus skev, okay, if you have two simple adrecs, like say 3 plus 4 or x plus 4, something like that, and something else, x plus 3, that's fine. But what if you have something more complicated? What if you have something with more stuff in it? Like it's just like a nested adrec, or let's say it's like there is a mul expression, there's like add expression, there's like, how do you handle all this? So that there are some cases that it handles. So if you're familiar with how skev works, skev is described in various papers, of course. It is actually backed by theory. There's not one paper for skev, but several papers that all describe the general idea of skev. So, you would ask yourself, is skev sort of, how do you recover that information from skev? How do you recover the indices from skev? So, this loop-access analysis is like quite simplistic in that regard. So the stride versioning is also there. In the case of a normal constant stride, which is what I talked about with loop versioning, it generates a version of the loop with stride equal to 1. And the strides are got from the adrec. It's as simple as that. It just says, get step. That's it. So skev, get step. And if you don't get the step, then sorry. I just don't know the stride. The other problem is that, yeah, it can only really analyze the innermost loop, which means that outer loops, any kind of thing that requires reasoning about some outer loop, some loop nest, some dependence that is carried between like loop nests, that it doesn't really do. Now, if you want to contrast this, of course, there is always the dependence analysis, which is not turned on by default, of course, but it has, the paper from 1991, the practical dependence testing. That's what it's based on. So that one is more dependence analysis for, in contrast, is more, how do I say? It's theory based. So it works in many cases. It is supposed to theoretically work in many cases. There is some MIV test, there is some SIV test. It's quite complicated. It doesn't do runtime checks. It just tries to say that, what is the dependence? That's it. And it is complete. It won't say that, oh, this is not vectorizable, so what is the point of telling you the dependence? It'll tell you the dependence. So the uses of dependence analysis are loop, unroll, and jam, and loop interchange, which are again not turned on by default because dependence analysis is not turned on by default. So to perform a loop, unroll, and jam, or loop interchange, loop interchange you can think about. There's like an outer loop, there's like an inner loop. You want to swap them. So obviously you need analysis of outer loops fundamentally, and unroll and jam also requires it. So what is the meaning of this innermost loop analysis, and where does it actually? Okay, I've been like fairly negative about loop access analysis, but let me show you like an example where it actually works really well. So this is an example where it works really well. You have an outer induction variable, you have an inner induction variable, and this is actually taken out of a test in loop access analysis. And it is aware of the vector width. So it can either generate runtime checks, or it can say that it is safe for a maximum vector width. So you have, I've cleverly put 32 as the start of the outer induction variable, so that it only goes to 33, 34, 35, 36, and then the inner loop only goes until from 0 to 256. So this is is possible to vectorize. Now, does it require runtime checks? Yes. If you don't have a certain minimum vector width, then it does require runtime checks. But otherwise, it doesn't. Let's look at some output of loop access analysis. This thing is, yeah, I mean, this is what it prints. It says that this is a forward dependence, and all the information that loop access analysis has within it is like printed in this debug output. You just say opt-pass is equal to access info, and it prints you this information. Now, this is a simple example. Let's look at a more complicated example. This is a more complicated example. So, in this case, it has now found some runtime checks that it wants to synthesize, that loop vectorize should synthesize. It has taken some skev expressions. It has shown the low and the high, that is the range of access, and it has also given you the equal predicate, that is the stride versioning, and some expressions that were rewritten by predicated scalar evaluations assumptions, which again will be used. So let's like summarize what are the issues with loop access analysis. It does not reason about outer loops. I mean, if you want to do multiple indices, you have to do something like dependence analysis, where you have to delinearize, the skev expression. But that's also not perfect. So the other route is basically a full-blown ILP solver, which is also not perfect because it blows up compile time. So there is really no good solution to all this. But what we can improve on is always false runtime checks and spurious false dependencies. These are things that we can engineer and we can make it better. We can not let it emit spurious runtime checks and false dependencies. And we can try to increase the number of contributors to loop access analysis. Like, it does require more eyeballs. It does require more contributors. It does have very few at the moment. So to conclude, loop access analysis is the analysis that we have, but we should ask ourselves, is it the analysis that we deserve? Thank you.
Thanks, Ram, for your presentation. Any questions?
Hello, thanks for the nice talk. I wanted to ask about the strength of skev. So is it something similar to a fine analysis, or can it do maybe more?
So it is a fine analysis, you mean like in terms of a solver, right? Somehow extracting out the multiple indices and like saying that each one is an affine expression, and then doing some kind of polyhedral optimization based on that. Skev is not that powerful, of course. It is not a full-blown solver, but it is powerful enough in practice. I mean, in practice, it gives you, like things that it does well are trip counts. So back-edge taken count, trip count, things like this. It does well. There are certain issues with it, like is known non-negative, is known non-positive. These things are not exactly, it's not like 100% there. It doesn't know some expression is like non-positive or non-negative, or is known 0. These things don't work super well. I mean, if there are some cast expressions, if there's something, it could trip over. So it is very much like something that doesn't blow up compile time, but is very useful in practice.
If you don't mind, another question. So what can you do if the arrays are not restricted or not with the restrict modifier? Yeah.
So if the arrays are not restricted, it's not a problem, because loop access analysis, like I said, would emit runtime checks for the aliasing part. And loop access analysis will communicate these runtime checks, and loop vectorize will insert these runtime checks in the pre-header. So it's not that your vectorized loop will get any slower. It's just that the pre-header, there'll be a small overhead of checking some at runtime whether they alias or not, and whether they alias within a certain range, within the range of vectorization or not. So as long as this is done, I think if you pay that small upfront cost, it'll vectorize perfectly.
Thanks.
So has there been any thought of combining this with dependence analysis? And the reason why I ask, I'm not super familiar with this pass, is your statement that it's more ad hoc versus built on theory.
So I'm not sure how to bolt on runtime checks into dependence analysis. That's the main cause for concern. But dependence analysis, I mean, at the moment, it's a very complicated piece of code. It's very large, it's complicated. People are trying to fix it, but there are still some outstanding issues in dependence analysis, I think. And we don't know if there is a way to move forward with dependence analysis, that is to actually, because see, if you when you're developing a new pass, the finish line is getting it turned on by default in the LLVM tree. Then if contributors, I mean, if it's turned off by default, then no active contributor wants to look at it, because it could be wasted time. So it depends on the community effort, really. But as far as I can tell, they are completely incompatible. They cannot be combined in any way. I mean, you can add runtime checks to dependence analysis, but that's also a hard problem.
Thank you.
Any other questions? Okay, then thanks, Ram, again for your presentation.
Thank you.